when you see a wave that looks like a slinky, like this one, that's called a longitudinal wave. Tudinal. Wow. So we have these two types of wave. We have longitudinal and transverse waves. And longitudinals look like this, and then transverse waves are that typical, like kind of up and down thing that you might be used to seeing. And then we also have mechanical waves, which are waves that require a medium, and then non-mechanical waves. And so you can have a longitudinal wave that is a mechanical wave, and you can also have a longitudinal wave that is not a mechanical wave. Same thing with transverse. You can have a transverse wave that is mechanical, and you can have a transverse wave that's not mechanical. So just because you have a longitudinal wave, that doesn't mean that it can't be that it can't require a medium and or a mechanical wave. And just because you have a transverse wave, that doesn't mean that that definitely is not a mechanical wave. So that mechanical term is not and longitudinal and transverse are not mutually exclusive. Now you can't have a longitudinal wave that is also a transverse wave. That won't make any sense because the longitudinal wave is about how it looks, not whether it requires a medium or not. So that's kind of an important point. And then for these longitudinal waves, we label different parts of it. So you can see right here, the wave is kind of squished up. And then also right here, the wave is kind of squished up. So those are the compressions. Okay. And I like to think the wave is compressed, right? Compressed means something is squished up. If you buy a compression sleeve or you buy like a Under Armour compression wear, right? It's tight. It squishes you, right? It squishes you up. So that's compression. A rarefaction are these spread out parts. Okay. And the way I like to think of it, if you think of the particles of the wave as being these little bits of slinky, right? The bits of slinky are more rare, right? Or less common, like that type of rare. So that's how I remember the rarefaction. You can also remember the rarefaction because it's the one that's not a compression, since there's only two terms for a longitudinal wave. So on your test or your quiz, it might ask something like, what is part A on the wave, or what is part B on the wave, or something like that. And then if you wanted to do a wavelength on this wave, it's from a wavelength, by definition, is from one part of the wave to the same part on the wave again. So if we wanted to do a wavelength here, if we started at the front of this compression, the wavelength would go to the front of the next compression. And this is our little symbol for wavelength. Okay, if we started here at the back of our compression, then our wavelength would go all the way to the back of this compression, right? So the wavelength is from the same part, from one same part to one same part. So if you start at the front of the compression, it goes to the end of the compression. So this wave right here, we've got this one, and then we've got one more, right? So this picture has two wavelengths in it. So that's a little more than I was going to go into, but I think it'll be helpful. Let's look at the next slide. Can you see this? Let's see. Okay. So this is a transverse wave. So transverse waves kind of look like mountains, where a longitudinal wave looks more like a slinky. I cannot get myself to write a V. There we go. Okay. And so then we can label different parts on this transverse wave. I'm going to start actually with the rest position. So the middle of your wave, which is like equidistant from the crest and the trough, which we'll get to, is called the rest position. And this really should be a flat line, but I'm not very good at it, at drawing perfectly straight lines freehand. So this is what we call our rest position. Sometimes they call it the equilibrium position. think they say that in the video, equilibrium. Okay. And then, so that's that rest position. Okay. Now the crest is the very tippy top of the wave. Okay, so both of these are crests. Okay, it's just your top of your wave. Okay. Then if you wanted to do your trough is going to be the very bottoms of your waves. So if you think of your wave as a mountain, the top of the mountain is the crest and the bottom is the trough. It's such a weird word. And then this one we can also do, we can say how many waves are there. So in this one, so your wavelength is from one point on the wave to the same point on the wave. So for this one, since we have the crest, if we go from crest to crest, that would be one wavelength. Okay, then I'm going to go from crest to crest again. That's another wavelength. I'm going to do it one more time. And I'm going to go from crest to crest one more time. And that's another one. And then we have this little bit out here, right, which is like half of the wave. So they'll call this, I think they call this like 3.5. And again, this picture is from your test. I'm not going to reinvent the wheel and try and make up my own pictures. So they might not ask you all of these things about this picture on your test, but you know, it gives you an idea of it's a good transverse wave. Okay. Let's go to the next thing. Okay, so you've got your formulas, right? You've got a formula, you've got frequency is equal to 1 over big T. And then you have your wave speed is equal to your wavelength over your frequency. That's bad. I would like, you can do like your wavelength over your sorry. So your I was like, wait a second, the formula for frequency, that doesn't make any sense. It's going to be your wavelength times your frequency, and we'll get to this in a second. We'll see why the units don't work. And or you could do like wavelength over T, your period. Okay. So your frequency, the units for frequency are 1 over S. And then we call this, nobody likes fractions. So we actually came up with something and we call this hertz. So if you have something that has a frequency of like 30 hertz, that's what that is. That's a frequency. And sometimes they'll just say 30 hertz wave, and you're supposed to know that hertz is your frequency. They might not say the frequency is 30 hertz. So it's important that you know the units, because then in your short answer problems, you can kind of pick out what you need. Wavelength is a distance, right? Length. So standard, we see the wavelength in meters, but sometimes you might see centimeters or something like that, maybe millimeters, but it's a distance. Your amplitude is also a distance, right? Your amplitude, let's see. Let's go back here. Okay. Your amplitude is the distance from your rest to your trough, or the distance from the rest to the crest. Okay, that is your amplitude. And so again, your amplitude is a distance. So it's going to be in meters usually. I think I saw a picture on your test that had it in centimeters, but it's going to be a distance like wavelength. Your wave speed. Speed, if you guys remember from Physics A, the standard unit for speed is meters per second. But I've also seen, for like small waves, I've seen centimeters per second. that kind of thing. Okay, so you can see if our unit for wave speed is meters per second, V is going to be m over s, then we're going to have to, we can't put frequency on the bottom, right? Because the s is on the bottom, which would then make it meters times seconds, which doesn't make any sense. And then our units for period are seconds. So period is a time. Okay, that's why it's got a big T. You can think of period as time. Okay, so that's why wavelength, which is a distance, over time, a period, seconds, right? That would give you meters per second, which are your units, right, for wave speed. So that's kind of how you can get those formulas. So if you know the units, it also is a way to kind of get the formulas. But remember, there is a formula sheet and you guys are allowed to use it on your test. So, go for it. It's not like you get extra points for, being an extra cool physics student and not using your formula sheet. It does not matter. You don't get extra points. So now this is also a picture. I don't remember if it's from a quiz or a test. It might be both. But anyway, they ask you the wavelength, the amplitude, and the period. So like, let's just do wavelength first. So if we want to go from, you see this front part right here, where we're heading up to the crest, to this front part where we're heading up to the crest, that's going to be your wavelength. So this is like what? 1.5, 4.5, what's that, 3? So this is like 1.5 in here. So our wavelength is 4.5 plus, I'm trying to figure out what this distance is. If this whole thing is 3, then this would be 1.5. So then our wavelength is going to be 6. And what are our units here? Sorry, we're doing wavelength. Centimeters. So our wavelength is going to be 6 centimeters. Okay, it's really important you put the units. Okay, if you don't, you lose points on a short answer. If this was a short answer and you just put 6, you would lose points, right? Because I need to know that you know the correct units. Then they say, I'm going to get to the frequency. I want to do these first. And then they get the amplitude. So the amplitude is right from your rest to your crest, or from your rest to your trough. Okay, so your amplitude is 4. Now look, the units here are different, right? 4 millimeters. Okay, so these two are different. Now, what is the frequency if V is 15 centimeters per second? So, right, we have this formula, V equals wavelength times frequency. And we found the wavelength, and here's our frequency, so or our V, so we can find F. And what I'm going to do is I'm going to go ahead and put it in the triangle. This is why I wanted to solve for wavelength first, by the way. And so my V is going to equal wavelength times frequency. Okay, and what do I want to solve for? I want to solve for frequency. So my frequency is then going to be V over wavelength. Okay, so then I'm going to do 15 over 6. Now, do you see how I have centimeters here? And I have centimeters here. That means that I don't have to do any conversions or anything like that. Okay, so now I'm going to put this in my calculator. I'm going to use the calculator on my phone so I don't have to bring it up on the computer. Let's see. 2.5. I think I'd be able to figure that out. Again, you don't get extra special physics points for not using a calculator. So, feel free to use a calculator on your test. So it's 2.5 hertz. Okay, so that's our frequency. I'm using this little like tablet pen, and I think it has a delay. And then the period, right? Our period is F equals 1 over T. Okay, so if I want to find T, again, I can put that in the triangle. You don't need to do any more work than you have to. So, don't bother doing algebra if you don't have to. I'm just going to make a 1 like that, and then a T, and I want to find T. So I'm going to do T is equal to 1 over F. So I just found out my frequency was 2.5, so I'm going to do 1 divided by 2.5. And I'm probably going to get a small number. I'm going to continue it down here. Math teachers would probably kill me for making all this mess. But I've seen your papers and you guys do the same thing. Okay, 0.4. And our units for that is seconds. Okay, so our period is 0.4 seconds. Now your test might not ask you to do all of these things from this image, but I wanted to go ahead and show you that way. Sometimes the questions, they'll have the same image, but they'll ask you different things, and so I just want to make sure you knew how to do anything they could ask you from this picture. Okay, so here's the next one. So if we want to solve for period, we have 12 waves, 12 waves passing a point in 48 seconds. So we have 12 waves per 48 seconds. Okay, so this is actually a frequency, this thing that they've given us. Okay, so we could even, I'm going to condense it a little bit. So I'm going to do 12 divided by 48, and I'm going to get 0.25 hertz. Okay, so then if I want to solve for period, remember our formula for frequency is 1 divided by t. So then I can put that in my triangle. F is 1 divided by t. I'm looking for period. Now, not every problem is going to say solve for period, but the reason I wrote them like this, like it won't say this at the front. The reason I wrote this is because I want to make sure I gave you guys an example of each kind. So that's why I did that. Okay, now it's coming back. It was lagged. Okay. So I'm going to do 1 divided by f. I'm going to do 1 divided by 0.25. And I should get a whole number, because anytime you divide by a decimal, you usually get a bigger number. So let's see. 1 divided by 0.25. I'm going to get 4. I should have known that. 4 seconds. Okay, so that's the period. So if this was multiple choice, I would choose 4 seconds. If this was short answer, I would show all of this, okay, because you get 1 point for showing your work and 1 point for the answer. So just writing 4 seconds gets you 1 out of 2 points, right? So if you want full credit on your short answer, show all of this stuff, okay? Let's go to the next one. Okay, this one is going to be a solve for wave speed one. So we have a wave with a wavelength of 5 meters and a period of 20 seconds. And this says, what is the speed? Okay, so we know our speed is going to be in meters per second. So sometimes I'll go ahead and like write this part. That way I don't forget to write my units later. Okay, so our formula is wavelength over our period. Okay, and since we've already got the formula in the correct, the way we want it, we can just do 5 divided by 20. And I know that this is something that I should probably know, but I'm going to go ahead and do it in my calculator because again, you know, you don't get like an extra special sticker if you don't use your calculator. Okay, 25. Yeah, see, that's something that I should know. Again, if this was short answer, all of this stuff would be worth 1 point, and this would be worth 1 point. Okay. And that's your answer with your unit. If you lost units, you'd lose half a point. Okay. Because it's important that you know the units. Okay, so let's try another problem. Okay, so this one we're going to solve for frequency. So it's telling us that our wavelength is 0.5. That's a pretty bad 0 meters. And our wave speed is 3 times 10 to the 8th. Now, this is actually our speed of light in a vacuum, which you'll learn soon enough that light is an electromagnetic wave and a radio wave is a type of electromagnetic wave. So this is a pretty common number. When we get to that section, they could just say a radio wave has a wavelength of 0.5 meters and not tell you the speed because the speed is something you're usually supposed to memorize. But if they don't tell it to you, that means it would be on your formula sheet. And then we want the frequency. So we know the frequency is supposed to be in hertz. Let me go ahead and do that so I don't forget. And then if you remember, our formula was wavelength times f. If you didn't remember, that's okay. You're allowed to have a formula sheet on your test. And we'll do V, wavelength, F. And so I'm going to solve for F. So then I'm going to do F is equal to wavelength over V, which is 0.5 over 3 times 10 to the 8th. Now, something that I've noticed that you guys are doing, if you are dividing by an exponent, which is why I chose this problem as opposed to one of the others that I saw, the numbers are different. So I don't think you've got the exact same one. If you try and put all of this in the calculator at once without putting parentheses down here, you will get the wrong answer. That's just, you will get the wrong answer. So when I type this in the calculator, I like to go ahead and put parentheses in the top and parentheses in the bottom. It takes like 2 seconds more to do that, but it, it ensures I get the right answer. Because, who wants to do all this work to do these problems and then not get the right answer, right? I feel like it's just a waste of your time. Okay, so I got a number with a lot of zeros. 1, 2, 3, 4, 6, 7, 8, which makes sense. Okay, so I got F equals 0.0000 5, 6, 7, 8. Okay, this is what I got. Now, you can leave it like that, or you can write 1.67 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the negative 9. If I think about that, that does make sense because we've got this huge number on the bottom, right? That's like 3 million, 30 million, something like that. And this small number on the top. So it makes sense if we've got a really big number on the bottom that we're going to get a really small number. So again, all this work, 1 point. The answer, 1 point. Okay, so make sure you show your work. Okay, here's another one. Let's see. We have a wave speed of 5 meters per second and a period of 10 seconds. Okay, and then we want the wavelength. And that's going to be in meters. Okay, so our formula is V equals wavelength over a period. And so if I want to solve for wavelength, I'm going to put it in the triangle. Thing hates drawing V's. And wavelength is what I want. So I'm going to have wavelength equals V times T. So I'm going to have 5 times 10, and I'm going to get 50. Okay, what do they call this in your videos? Plug and chug? Isn't that what that lady says? So again, 1 point. 1 point. Okay, so make sure you show your work with the units. Okay, I feel like I'm saying this over and over, but, well, I am. But I want to make sure you guys get it right. So let's talk about waves hitting boundaries. So if you can think about like waves in a pool, right? If this is a pool and like, let's say you threw a rock in, okay? Your rock's going to go and you're going to get these like things like this, right? Getting bigger and bigger. And then when they hit, then it's going to bounce back and keep going back, right? So when a wave hits a boundary, whatever it is, when it hits that boundary, it's going to bounce back and then travel along there. Okay, so like we used to do this lab with my students with slinkies. So we would have a student here, and we'd have a student here. We had these huge slinkies, springs, I guess. And we'd have it, and then we'd have one person hold it still, and the other person would like flick their arm to make this bounce, right? So then we'd have this wave going like this, and when it hit this kid, the kid would feel it, and then the slinky, that energy would travel back over here, hit this kid, travel back over here until it, slowly getting lighter and lighter and lighter until it, just kind of died out. So when waves hit boundaries, this is energy, right? So the energy is hitting this wall. It's going this way. It's going to hit the wall, go back this way. It's going to come back smaller and smaller. So like if this was our wave the first time, then the next time it might be like this, and then, like this, and then eventually it would just be flat. Okay. So when waves hit boundaries or they hit something, they're gonna bounce back until they run out of energy. So this is a picture from your test. I really don't like this picture. It bothers my eyes. See, I feel like it's moving. It looks like it's moving to me. I just, the more I see it, the more I don't like it. But basically what they've got is they've got two kind of bullseyes, and they're like overlapping each other. And so that's kind of what you're seeing. And so this is called interference. I don't think it's a great example of interference. I mean, So it's kind of confusing, and so I wanted to just go ahead and show you guys that. I'm gonna go away from that page because I don't like it. Now let's say that we've got a wave, and we have one student over here. They're sending a wave pulse this way, right? And then we have another student over here, and they're sending a wave pulse on the slinky this way. Okay. When these two waves meet, okay, because they're both, if you think about it, on top waves, if this was the rest position, right? Both waves are like on top waves, if that makes sense. They're going to add together. So you're going to have this plus this, and they're going to get, if this would say like 1 unit tall and this was like 2 units tall, then this would be like 3 units tall, if that made sense. So they call this constructive interference because they add together. Okay. So this is a way you can get something to be louder or get harmonics that kind of, anyway, like kind of like the bridge example they were talking about in the video. So we've got, if they're constructive, they're going to add together. This next page, we'll do destructive. Okay, now if they're destructive, they're going to subtract. Okay. Okay, so let's say we've got one student is sending a wave pulse this way, another student is sending a wave pulse this way on the slinky. When these two meet, right, one's above, so they do kind of, I guess, add together, but it's kind of like this one's a negative. So if this was like 1, say it was like 1 unit tall, and this one was like negative 1 unit tall, then, you'd get just like a flat line. And this is destructive interference. So constructive interference, they add up to make the wave more powerful than it was in the first place, than either of the other ones. And then in destructive interference, they add together to make something that is less powerful or smaller than either of the two initial waves. So now this is this is one of our formulas. It's in the videos. We'll talk a lot more about this when we get to sound, but they discuss it a little bit here. I always call these harmonics, but some people call them overtones. I think the video and the test call them overtones. You can call them resonances, like where will it resonate. Like for example, like when I would study instruments with my students, we would talk about like the first harmonic or the second harmonic. That's what these are. Okay. And what they are for right now is the first harmonic is just whatever your frequency is. The second harmonic is 2 times that frequency. The third is 3 times that frequency. The fourth is 4 times, and the fifth is 5 times. Now, when we get to open and closed pipes, you'll see that some of them they work a little differently. But on your test, right, they could ask you. So if your F is 500 hertz, right, and they could ask you, what is F10, right, or the fifth harmonic, or the fifth overtone, or the fifth resonance, or whatever they want to call it. So if this is 500 hertz, then your second frequency would be 2 times 500, which is 1,000, right? They could do 3 times F, And actually, one of these is the one they ask you in the test. I just did a bunch of different ones, so I wouldn't be giving the answer away exactly. I'm just going to draw a new 3. 3 times 500. Right, so that's going to be 1,500. If this was a short answer, you'd want to show this work part, even though it's simple. You'd want to show it. And there's a couple reasons, by the way, that we want you to show your work. One is because then we know that you know how to do it. But 2, if you don't know how to do it, it's easier for me to see where you went wrong and to help you and to help you fix it. Like, because sometimes I can tell that you might have just forgotten a parentheses, or your work is all right, but instead of 1,000 you just wrote 100. Well, you just forgot to write that last 0, right? That doesn't mean you don't know what you're doing. But if you had just written 100, then I would have gone, was she dividing by 2? Was she dividing by 500? How was she getting this, right? How is she getting this 100? Where if you did 2 times 500 and then you wrote 100, I'd go, oh, okay, he or she just wrote the wrong thing. So that's why if you guys will notice on your classwork, on your assignments, if you get the wrong answer but you show your work, I go ahead and I give you full points for showing your work, even though technically your work wasn't the right work. And that's because by training you or teaching you to show your work, and giving you credit for showing your work even if your answer wasn't right, you guys get in the habit of showing your work, and then if your answer's not right or you did something wrong, it's easier for me to tell what you did wrong. Because if you don't show your work, I have no idea where you went wrong. There are a million ways to mess up, right? And so by showing your work, it shows me what you did wrong and how we can fix it. So I'm not just trying to be like a total jerk. It actually helps you out, because if I didn't give you credit for showing your work, then if you got the wrong answer, then you'd get like 0 points instead of at least just a few. So these are how we do our harmonics. Okay, like this: 1,000, 1,500, 2,000, 2,500. And it's just, if we wanted to do, if they said like, what is F20, right? You could do F20. You could do 20 times 500. Okay. They're not going to ask you F20, but they could, right? And you'd know how to do that, because it's just, whatever this little number is down here, that's what you multiply your initial frequency by. They could also do something where they say like F5 is equal to 2,500. What is F1? Right? They could do that. And it wouldn't be terrible, because F5 equals basically 5 times F1. So we could just divide 2,500 by 5 and get, 500. So they could ask you a question like that too, and that's totally fine. You can do it. So those are those frequency ones. And again, we'll get way more into this when we get to sound. This is just kind of a cursory overview. When I taught this in the face-to-face classroom, I actually put this